Let's take a look at problem 12.3. In this problem, we have a machine that uses a pair of concentric helical compression springs which support an essentially static load of 3 kilonewtons. Now, in the statement here, it tells us we're dealing with a static load, and it also tells us which type of spring we're dealing with. We're dealing with concentric helical compression springs, and we know that there's a pair of them. There's going to be an inner and an outer one of these springs. Both of these springs are going to be made of steel, and they're going to have the same length when they're loaded versus when they're unloaded. So we know when we load this guy down, it's going to deflect the same amount in the outer as the inner spring. Now, the outer spring is going to have a capital D of 45 millimeters, which is going to be the outer coil diameter. Our diameter of the wire for the outer is going to be 8 millimeters, and our N is going to be 5, where N is the number of active coils. So now we're going to have the same information for our inner spring system down here, where the inner spring is have a coil diameter of 25 millimeters, and we have a wire diameter of 5 millimeters, and N equal to 10, where N again is the number of active coils. Now, what are they asking us to solve for? Well, they want us to find the deflection and also the maximum stress in each of these springs, the inner and the outer. So here is the given diagram. So we have a side view and a top view here. So we can see our load here, 3 kilonewtons. Then over here from the top view, we can see, okay, if we look here at our inner, we have our big D sub I, so which is the diameter of the coil, 25 millimeters. We have our little d sub I, which is the diameter of the wire, 5 millimeters. Then we can look at the outer coil here, and we have our big D sub O, which is the coil diameter of the outer, 45 millimeters, and we have our little d sub O here, which is our wire diameter of the outer, which is 8 millimeters. So now that we've had a chance to read through the problem statement and look at the given diagram, the next thing we want to do is identify all of the information that's given to us in this problem statement. So what we do here is we write down all of our variable names, what our values are, our units that we're dealing with here, and how they relate to our problem. So we know for this problem is we have a pair of concentric helical compression springs, and these are going to be steel springs. So they're going to be made of steel, so it's going to help us when we know where to look things up. First thing we have here is we have our static load given to us in the problem statement is F. F is equal to 3 kilonewtons. Then we have our outer coil diameter, D sub O, is equal to 45 millimeters. Now we have it in millimeters here. We may want to leave it in millimeters or convert to meters. It's up to you. It doesn't hurt to do it right here and have both right in front of you to reference back to. Then we have our wire diameter for the outer, little d sub O, which is 8 millimeters. We have our number of active coils for the outer spring, which is 5. We have our outer coil diameter, d sub I, big D sub I, is equal to 25 millimeters. And we have our wire diameter for the inner, which is 5 millimeters. We also have our active number of coils as 10 for our inner coil. Now, we can redraw out our diagram here, take a look. Essentially, it's the same as we saw back in the actual given schematic here. But again, now we have our inner and outer diameters of both coils, our wire diameters. We have our external load here. So we kind of have a good visual of what's going on right next to all of our variables and the values. So the next thing we want to do is see what they're asking us to solve for. So they ask us to find the deflection and the max stresses in each of the springs. So there's 4 things essentially we're solving for when they're asking this. Deflection in both springs, and the stresses in both things. But if we go back to the problem statement, we recall that it tells us this deflection is going to be the same because the spring distances are going to be the same, the amount of compression loaded and unloaded. So that deflection is going to be the same for both springs on this. So these should be equal, which is going to help us in our solution as well. Now, from there, what we want to do is come up with our assumptions. So there's 3 assumptions that we're going to make for solving this problem. First one, no unfavorable residual stresses. 2, both end plates are in contact with nearly a full turn of the wire. So it's going to be in a full turn of that wire is going to be in contact with that loading plate. And then the last assumption is that the end plate loads coincide with the spring's axes. So we can go to page 352 of our textbook and take a look here at equation 12.8. So we can go down to 12.8 and we can see this here is a spring rate. also called the spring constant or spring scale, with units of newtons per millimeter or pounds per inch, etc., commonly designated as K, where we have now this relationship here, where K is equal to our static load over our deflection, which is equal to a lowercase d, which is our wire diameter, to the fourth times constant G, which we're going to look up from a table in the back of the book for steel, and then we're going to have divided by 8d, which is capital D, which is the coil diameter to the third, times N, which is our number of active coils. So this is where we get this relationship from equation 12.8 for our K value here for our spring. Again, lowercase d, uppercase D, G for our lookup from the back, which we're going to get to next, and N for a number of active coils here. So where G comes from our appendix C1. So we're going to reference back to appendix C1 for steel in this case here in order to get this value. So if we go to appendix C1 in the back of our textbook, we find a table for the physical properties of common metals. You can see all the different metal types on the left-hand side over here, all the different properties going across the right. So what we're looking for is our modulus of rigidity, which is our G, which we're looking for here. And we're dealing with units of pascals for our case here. So we go down in our material or metal over here to our steel. Then we come across over to our modulus of rigidity, which is under GPa, and we find that this has a value of 79 GPa. So now that we've got our value for G, or modulus of rigidity, from appendix C1 for steel in the back of our textbook, we have this as G is equal to 79 times 10 to the 9th pascals as we go from gigapascals to pascals. We can take this along with our other known values and go back to equation 12.8 and start plugging in. We wanted to make sure that we do this for both the outer and for the inner separately and come up with a separate K value for each of those. So we do this for the outer first. Our DO, our wire diameter for the outer, is 8 millimeters. Our big DO, our coil diameter for the outer, is 45 millimeters. And our NO, our number of active coils for the outer, is 5. We can plug this into our 12.8 equation. K sub 0, or K sub O, is equal to 8 millimeters to the fourth times 79,000 newtons per millimeter squared. And see, we're dealing with millimeters here, not meters. Divided by 8 times 45 millimeters cubed times 5 for our N of 5. Plug this in, and KO is equal to 88.77 newtons per millimeter. Now we do the same for the inner over here, where DI is 5 millimeters, our inner wire diameter. Big D sub I is 25 millimeters, our coil diameter for the inner. And N sub I is 10, our number of active coils for that inner. Plug those into 12.8. K sub I is equal to 5 millimeters to the fourth times 79,000 newtons per millimeter squared divided by 8 times 25 millimeters cubed times 5. Plug this all in, our K sub I is equal to 39.5 newtons per millimeter. So now that we've gone through and solved for our K value, the next thing we want to do in our solution is solve for deflection. So we can still go back to our equation 12.8. We have that K is equal to F over D, where K is our spring constant, F is our static load, and D is our deflection. We want to rearrange this expression now and solve for deflection. We do that and find that deflection is equal to our static load divided by K. Now, for our problem here, our K is going to be our combined K value because you have an inner and an outer spring that are both loaded, and we know that the deflection is going to be the same for both the inner and the outer spring. So it's going to be the combined K value as we plug into this relationship. So we plug in our known values. Deflection is equal to our static load of 3,000 newtons or 3 kilonewtons divided by, we're going to add both of those spring constants together here, our 39.5 newtons per millimeters plus 88.7 newtons per millimeters for the inner and the outer. We do our math here, and we find the deflection of both springs is going to be 23.39 millimeters. So the next thing that we want to do is get our K sub S values for the springs, where K sub S is the stress concentration factor for static loading. Now, we can go to figure 12.4 to the chart there and back out our K sub S values from that there. But in order to do that, we're going to need our C value, our capital C, which is the ratio between our diameter of our coil and our wire diameter. And we got a different one of those for our inner and our outer coils here. So for the outer, our C value is going to be D naught over lowercase d naught, which is 45 millimeters over 8 millimeters, which gives us a value of 5.63. Now for the inner, we have a C value of di over d lowercase di of 25 millimeters over 5 millimeters, which is 5. So we can take these two values here and go back to our chart 12.4 in order to get our K sub S values. So now we go to figure 12.4 in our textbook, where this is the stress correction factors for helical springs. So we look here at our axes, and down the bottom we have our spring index of C, which is the ratio of our coil diameter over our inner wire diameter there. And on the y-axis we have our KW and KS over here. And now we have our separate curves as we go up along here for which we're looking for. So what we want to do is come on our x-axis down here and enter our value for our outer, which is 5.6 when we plug those into the equation. Go up to our K sub S line here, come across, and we get a value of 1.09. Now we do the same thing for our inner, which has a value of 5 for C. We go up here to our K sub S line again, go over to the side, and we have 1.1. So now we have our capital K sub S values, or correction factors here, that we can plug back into our equation. So we're able to go to figure 12.4 to that chart there and get our K sub S values or correction factors here for our outer and for our inner. So K sub S for our outer is 1.09 from that chart. K sub S for our inner is 1.1 from that chart there. So then what we can do is we can reference back to equation 12.6 on page 351 of our textbook. And what we can use this for here, this is our corrected stress equation for static loading. So we want the corrected one so we could use these K sub S values we just found from figure 12.4. Now our governing equation 12.6 from 351, tau is equal to 8FD, capital D, divided by pi, lowercase d cubed, times this correction factor K sub S. Now again, we want to do this for inner and for outer. So we rewrite out all of our known variables, or we can flip back to our first page. Our load that we've just solved for here, F sub I, for the inner is 924 newtons. Our D sub I capital is 25 millimeters there, and our lowercase d sub I is 5 millimeters. Now for our outer, we have 2,076 newtons for F sub O. Our D sub O capital is 45 millimeters, and our D sub O lowercase is 8 millimeters. So we have all the information we need now to plug back into equation 12.6 to solve this out. So I want to do this separately for the outer. We plug in our values here, 8 times 2,076 times 45 divided by pi times 8 to the third will give us a value of tau outer of 506 megapascals. And again, pay attention to all your units you're plugging in here to make sure your final units are correct and do out your unit analysis. Now we go down and do this for the inner. Tau inner is equal to 8 times 924 times 25 divided by pi times 5 to the third. Do out the math here, and our tau for our inner is equal to 518 megapascals.